Hi, welcome back to the lecture series on GPU architectures and programming. So, in the last lecture we have been discussing about some algorithm which can perform parallel computation of prefix sum, and we argued that why this algorithm would work, but let us look at also a picture which kind of just signifies and highlights the properties of the algorithm we discussed. That initially in step 1 it is adding elements at steps of at a stride of 2 to the power 0, then 2 to the power 1, then 2 to the power 2, and like that. So, in each iteration the number of threads that are active is decreasing from n minus 1 to n minus 2, n minus 4, n minus 8, like that. The number of steps here is the log n, of course, because that is depth. And what would be the analysis here? First problem is that sequential scan performs order of n adds, and this implementation apparently seems to be naive, because we also have that many adds here. And if we are, but what is the more important point here is that if we are trying to implement this directly in a just the way we talked about the loop, if we just implement this kind of a loop in form of a CUDA program, it is not going to work. Why? First problem is, here we are assuming, it seems like we are assuming that we have as many compute cores as are the number of active threads. Why would I say that we are assuming that? Because you see, unless we assume that, we are going to have a problem. Why? Because in case it is not so, for example, in a GPU that is really not going to be so. Considering a big array, you have launched lot of such threads for doing this prefix scan operation, and you do not have many threads. So, you are now going to the processor, when it is trying to implement this for a loop in parallel, that means it is going to, I mean, how will really you execute this as a CUDA program? The first thing you will do is you do not have such a parallel loop. Instead, you have a kernel, where inside the kernel you would have only this. So, this first of all, this is not a representation of the CUDA code. This is just like a way we are trying to tell that how the parallel algorithm would work, right? I mean, that is something we will like to make clear here. We will say that this is a for a loop. Inside the for loop, I am trying to say that this is the activity that is going to happen in parallel, right? But when we talk about the corresponding CUDA implementation, we do not have something like this. We just define a part thread activity, and the part thread activity will be defined that, okay, each thread will be executing this outer for loop and this statement, right? That is how it will work. So, then we will be launching those many threads in parallel, and they would be divided into warps, and those warps are at the mercy of the hardware scheduler, because the warps will be scheduled based on the hardware scheduler's algorithm, and we do not have any control that which warps goes fast and which warps get slowed down, right? And but due to that we will also have problems. What is the problem? The problem is that the results of one warp can get overwritten by the threads of another warp, right? The reason being, here the way we have presented the algorithm, things are happening in place. So, as you can see that we are writing, every thread is writing its results on the same array, right. So, the moment this computation gets divided across warps, there would be locations where you need data across warps, right. So, unless we have some synchronization primitive, or we have some way to control that how the warps interact among each other, this naive implementation, if I just do a parallelization here in a naive way, where I mean where every warp is working in place, things are going to be very bad. So, what is the option in that case? How can I really make the warps work in such a way that they do not overwrite results computed parallel partial results computed by other active warps? One option is that, again, we are just writing the pseudocode here, right. I mean, we are trying to give the activity description which you have to implement as a CUDA code. let's first understand that how this scheme will avoid that problem. It's called a double buffered version of the algorithm 1. Why double buffered? In the algorithm 1 example, we just showed the in place implementation, which we argued that it's not going to work in case of work based scheduling of the GPU. If we consider this double buffered implementation, we are saying that, hold on, let's consider that we have two such arrays, in and out. Updates by the thread will always happen on the out array. So what we'll do is, first thing we'll figure out what is the depth. So in the CUDA code, this thing will not be there, right? This is all parallel activity. This is the per thread activity. Every thread falls into the loop. In the loop, first it has to figure out what is the depth at which it has to be operating. If the depth is 1, you have n minus 1 threads working. If the depth is 2, you have if the depth is 0, you have n minus 1 threads working. If the depth is 1, n minus 2 threads. If the depth is 2, n minus 4 threads, like we have already discussed, right? So that decision is taken by this condition, right? So based on the depth, I have inactivity at certain parts, and threads starting from the rest of the positions are going to work with this much of stride, right? So this value is actually deciding what is the stride, as we have already discussed earlier, that the stride is equal to, n minus stride is the number of threads that would be working, right? But what are the threads going to do? They are going to consider the data values from the in array and do the computation and updates on the out array, right? So the threads will do their computation on the out array. If the threads do not belong to the portion where we are doing the computation, like if we go back, if the threads are here, if the threads are from here, with three IDs of here, then at some stage they are not going to work, right? For example, this thread will stop working here. Only these threads will remain active. This thread will stop working after d equal to 1, right? So that is the condition which is being signified by this if, and then inside this if we are saying that, okay, just do the same thing, just copy data from in and do the updates in the out buffer. If you are not in the working set, the thread ID, then don't do anything, but still just completely update things in the out buffer, right? So the thread either computes, that means does the addition, or it just updates data from the in buffer to the out buffer. At the end of this, you do a swap, that means exchange the values from the in to the out. That means after this, you have a consistent view of whatever this threads has done in the in buffer once this loop is processed by some warp, right? So in that way, now the earlier problem can be mitigated and we can have a CUDA implementation. So this would be the CUDA code here. So as you can see, so here this is the loop inside which the above computation we discussed would be done. So the thread ID is first checking whether it's beyond the offset or not. In that case, it would add. Otherwise, it will just simply copy, right? We are discussing here at a high level. Every thread would synchronize at the end of the iteration of the loop. That means every thread synchronizes with all the operations inside one depth level, and then the entire loop goes to the next level, right? Like that. Once the entire loop is traversed by the threads in the warp, they are just going to copy back from out to in, right? And then again, some other warp which is progressing, if they require the data, they will get the data from the modified in, right? So this is how this algorithm is going to work. But yet we can say that this algorithm can be further improved by using a better technique where we have to do lesser number of adds. So let's see that how a possible improvement can be done. So this is possible using this Blaloch scan technique. Here the idea is to build a balanced binary tree on the input data, and you sweep it to and from the root. So you first do a normal reduction, and then you do what we call as a down sweep. And if we do that, essentially after the down sweep operation, we can get all the prefixes computed. We will see with an example what we really mean here, and it should be easy for us to actually mark out the advantages out of this method. So this algorithm will have two phases. In the first stage, we have a normal reduction phase, just like a normal reduction computation. If we assume addition is just like the normal reduction addition examples we did earlier. So we traverse the tree from leaves to root, computing partial sums as internal nodes of the tree. Now, why suddenly have we started talking about the tree? Essentially, if we look at a reduction operation, and if you want to create a sequence of operations, we can say that, well, we are first doing computations at stride equal to 1 and then stride equal to 2, like that, and that I can represent in the form of a tree. So let's say these are the initial nodes. We are just trying to draw a normal reduction picture here. So you do the sums. These are the local sums we are doing. Right? Then you go one up. Effectively, this is what you are getting, right? If we just try to create a graph here based on how the values are flowing, then essentially each thread does a computation at stride 1. Then you do a computation like this, like that, right? So I can say that thread ID, all the thread IDs would progress like this. This is the initial computation, and then the way I am organizing here, I am trying to say that, okay, then these two values are going to be added like that. I mean, this is one way of looking at it, right? But then at the end of the reduction phase, what do we really have? Okay, let me just redraw it again. So if we create a tree of this computation, at the end of the reduction phase, we have the overall sum sitting here, right? So after this phase, what we will do is we will do a down sweep. That means, in terms of the data structure, we traverse back from the root to the lower level, and what we do is, so whatever initialize this root with a 0. Suppose I have some value here, val 1. So I will copy this value here, this value comes here, and this val 1 plus the existing value here goes to this point, right? So if I draw a better picture, I will start with the root being initialized to an identity. If it's addition, then it's a 0. We pass it here, and whatever the value was here, you add it up with this value and put it here. So in general, if I say this is val 0 and this is val 1, you put val 0 here, and here you add val 0 and val 1 and put it here. So this is the operation you keep on performing downstream to get the final prefix sum computed, and it really works. So let's see how it works in terms of a parallel implementation. So good idea would be to look at the picture here, because it would convey the situation clearly. So first of all, what do we really have at the end of a reduction phase? We understand that at the end of a reduction phase, at this position, we would have the final sum computed of the entire array. Now if we look at the different phases of reduction, so like this is the tree structure I was talking about earlier. So considering these as the lower level nodes, I can say that here I have computed I have computed an intermediate value, right? These values are again getting summed up by this thread. Again, these are intermediate values. They are getting summed up here, and I am creating a tree like this, with this being the node, root node containing the entire sum, right? Now, just try and observe what are the partial sums that we have right now. So, at alternate locations I have no sums, but just the value corresponding to that location at alternate locations. And the other alternate locations, what I have is the partial sums, right. So, here I have summation up to x7, alternate location I have summation up to x5, then in the alternate location summation up to x3, summation up to x1. I have to figure out a smart way such that I am able to compute the prefix sums for, of course, the only prefix sum which is ready with me right now is this, and of course, the other alternate locations, because this is also a prefix sum, valid prefix sums are there, right. So, we have them ready, but what is not there is the prefix sums in the alternate locations, which I have to figure out efficiently, right. Now, the way we will do it is, as we explained earlier in this picture, that okay, we will do a down sweep and perform the operation that I just defined, that start with the identity from the root, copy that in the left child, take the left child's value and add with the root's value and put it in the right child. And let us see that why that works. First, let us just observe the figure. So, what we will do is here in the down sweep phase, we will put the identity here which is 0, and then we push back the 0 here, okay. And then, so this is the input of the down sweep phase. First thing we do is we remove this, and we will just remember this and push a 0 here in the down sweep phase and put the 0 here. So, this is the left child where we copy the value, and what was the original content of this location? It was x0 up to x3. So, do an addition with this value with x0 to x3 sum. So, in that way, in the right child you put in the summation x0 to x3, right. Just repeat this thing in parallel, that is the good thing we are going to do. So, again from these points where we made the modifications in the tree, you just keep on doing the same operation. So, you again copy the current locations value, which locations? The locations which you, where you just made the updates, the left and right childs, you copy it to the left child, whatever was the left child's value, the summation x0 to x1, add it up with this value that you just copied, put it in the right child, right. So, that would give you the summation x0 to x1 here and give you a 0 here. If you propagate it, you get the 0 here, and essentially here you are adding 0 with the x1 that was already there, right. 0 with this we would give you x0 here. When you copy from here, you put in x0 to x1, and the right child's value that was originally there was x2. So, you just add the right child, the left child's value and put it back to the right child. So, this is what you get. Again, I will just repeat the algorithm. What you are doing, you are copying the value from the root to the left child. Let me just redraw these locations again. So, you are propagating it here, and what was the original content, this one, you are adding it out with this and putting it here. Just follow this, you are propagating it here in the left, whatever was the original content, this was the original content of the left, right. You add it up with whatever you propagated and put that updated value to the right. Now, you see why this works. So, you have propagated x0 to x3 and you are adding up this with the original content which was up to x4 to x6, x4 to x5, and in that way you are getting summation x0 to x5 here, right. You are putting in summation x0 to x5 here, you are adding it with the original location x6, and here you are getting x0 to x6. Again, if I look here, so whatever you copied here was summation x0 to x3, you copy that to the left child x0 to x3, original content of left child was x4, you add it up to get summation x0 to x4, right. So, if you just follow this operation, at the end what you get is basically an exclusive scan, right. So, 0 x0 x0 to x1 like that up to summation x0 to x6, right. So, in this way, with this parallel sums getting computed, you end up the alternate locations prefix sums being computed. You already had something here x4 to x5, then x0 to x3, x0 to x1, x0 to x7 like that, but now you have for every location it done. So, initially after the reduction phase, your status was only for the root for the last location, or I would say the root location of the tree, you had the total sum done, that was the correct prefix sum for that location, but for the other locations there were sums which were actually for certain substrings. So, for a sequence of locations, and in the alternate locations you just had individual values, right. But by doing this operation, you are now able to get, when the downsweep phase ends, you are now able to get a continuous sequence of prefix sums for the entire array. So, I would just repeat the operation that we did. Once this value is this computation of the reduction phase is done, reduction phase gives you the prefix sum only for the last location, and for the other locations you have at alternate locations only the value that was there, and at alternate locations you have some subsequences sums that have been computed, right. So, now you start the downsweep phase. So, you initialize this last location with a 0, and you start propagating this to its left child, and whatever is the content of the left child, add it with whatever you propagate and put it in the right child, and in that way when you end the downsweep for the requisite number of depth, so log n depth, then you end up getting the array filled up with the actual prefix sums. Okay. So, if you just look into the parallel pseudocode here, so essentially you are running this loop up to log n depth. Inside each iteration, depending on the depth here, what you do is essentially you are storing the current location's value to a temporary variable, then you are propagating this value. So, you are storing sorry, this is the left child's value which you are storing in the temporary variable. Then in the left child you are storing the current location's value, and then in the right child you are updating with the current location's value, which is this, and the previous remembered left child's value, the operation that we just discussed, and this is going to happen in parallel inside a depth, and then we are going to go to the next step, just like the picture. So, now we have a overall picture of the Blaloch exclusive scan. So, as you can see that we have the reduction phase done. At the reduction phase end, I just have this location containing the inclusive sum value, but for the others I just have either the original values, or I just have a subsequent sum value, and then I perform the downsweep starting this location with 0 and actually utilizing all the other location values, and we see that in parallel we are able to compute the value for the prefixes as an exclusive scan at the end. So, just a representation of the CUDA code here, which would be easy for you to figure out, given that we have already discussed that what exactly is going on. So, this is the loop where you are performing that. So, this is basically the part where you build the sum through the original reductions here, right. So, this is the part where you are doing the reduction. I mean, we are not getting into the details here, it is kind of repetitive, and then once the reduction is done, this is the next loop where we are performing the downsweep. As you can see, this is where we are performing that operation of getting values from the roots to the left child and adding up the left child values with the right child and updating the right child, and at the end doing a sync thread across all the threads in the block, and then finally updating the global memory. So, with this we would like to end our discussions on certain parallel reduction algorithms. So what we have, we like to end up with the following conclusions, that we try to understand the performance characteristics of these different optimizations, like how memory coalescing, handling divergent branches, resolving branch conflicts, and trying to hide the latency by making more threads do their work makes sense, and to create performance aware programs. So we explored all these techniques in the context of parallel reduction, and then we also started looking into other parallel algorithms as an example and their corresponding CUDA implementations. What we didn't really do is explore how, what are the performance issues in those algorithms. We'll actually leave those for people who are interested, and maybe some of those will also be part of our assignments. So these are the issues we have to think, right? That how to make the other algorithms that we discussed performance aware. How to create low latency versions of those codes. What are the issues with those codes? What are the good and bad things with respect to memory operations, latency, cache conflicts, or whether they really have some bank conflicts and all that. So please look into those aspects for the other algorithms that we discussed apart from parallel reduction, like the ones in Bytonic sort and also the one in prefix sum operations. And with this, we would like to end this topic, and in the next lecture we will be starting a new topic here. Thank you for your attention.